Origins of Quantum Theory. This is part of Module 8 in the HSC Physics course. So let's go back to pre-1900. So before the birth of quantum theory or quantum physics, same thing really, physicists believed that something called a black body. So a black body is an idealized object. Idealized means perfect, that absorbs and emits all wavelengths of light. There's no such thing as an idealized black body in the real world. It doesn't exist. There's no perfect absorber or emitter of all wavelengths of light, as far as we know. Okay, to an approximation, stars are. Things like stars. So what physicists before the year 1900 believed was that a black body should emit more and more energy at shorter wavelengths. In other words, you can go as high energy as you like, okay? Forever. High and higher frequencies. And according to classical physics, as the wavelength, okay, the distance between two peaks, two crests on a wave, as the wavelength lambda approaches zero, the energy output should go to infinity. Now, this doesn't happen in real life. According to classical physicists, this is the case. It would be unsafe to sit in front of something like a fireplace or an oven. Okay, we can't, there's no way you can get an infinite amount of energy. It's not possible. Now, this was called the ultraviolet, the UV catastrophe. And the Rayleigh-Jeans law demonstrates this. Now, Rayleigh and Jeans, Lord Rayleigh and James Jeans were two English physicists who came up with a law just after the year 1900, and it failed at high energies. So if I was to draw a graph of, let's say, wavelength and energy, or intensity, let's say. Now, for a black body, this is what you get in the lab. Okay, so physicists were trying to find a theoretical explanation of what was happening. You get a range, you get a spread of energies. And the peak intensity happens at a particular wavelength. Now, Rayleigh and Jeans, their law worked really well at low energies here. Remember, increasing wavelength, you get low energy. Decreasing wavelength, you get high energy. However, it failed, it diverged at higher energies, shorter wavelengths. Okay, that's it there. And there's another law called the Wien law, after Wilhelm Wien, German physicist, that worked really well at high energies but failed at low energies. Okay, so Wien's theory did this. Worked great at high energies like this, but it failed. So neither of these two curves really worked. Then along came a guy named Max Planck, a German physicist who saved the day, also known as the father of quantum physics. He started it all, Max Planck. And he proposed in 1900 that, unlike the classical physicist, energy isn't emitted continuously. Energy comes in chunks. So think of a wave. Classical physicists believe that black body radiation looks like that. It's a wave. Planck said, yeah, okay, sure, but it's broken up into chunks. Discrete packets, it's quantized. Quantized means discrete. Think of little beads. Okay, think of a necklace. It's got beads. So it's a great model right there. Okay, these are called quanta. These quantized discrete packets of energy. Quanta is plural for quantum. And the energy of each quantum is given by the following expression. It's very simple. E equals hf. Now, h is a constant. It's now called Planck's constant in his honor. 6.626 times 10 to the minus 34 joules seconds. E is the energy of the quantum, measured in joules, and F is the frequency, measured in hertz. Okay, this expression here kickstarted the quantum revolution in 1900. And Max Planck's mathematical model worked brilliantly. He was able to fit his model to the data, and it worked really well. And what he got was almost more or less a perfect fit to that black body radiation curve. Now, these quanta, known as photons as well. Okay, a photon. The name photon was coined much later on by another guy named Gilbert Lewis, but anyway. So this means that to emit a high frequency, in other words, a short wavelength light, you need to have more energy. So in other words, high frequency photons require more energy because E equals HF, right? High frequency, high energy. Okay, this is why I tell students all the time, if you look visually, one wave here, another wave there. This is why, let's say that's UV light, and this is visible light. That's why UV gives you skin cancer, God forbid. Because there's more peaks, more crests, high frequency, than visible light. But at normal temperatures, let's say room temperature, the atoms in a black body, they don't have enough energy to emit these high frequency photons in large amounts. Okay, they're extremely rare because the intensity drops off here at low energies. Okay, that's why it's called the ultraviolet catastrophe, the UV catastrophe, because for the Rayleigh-Jeans law, because it fails at high energies. So instead of infinite energy at short wavelengths, you see a peak intensity at some intermediate wavelength, and it drops off on both sides. Okay, so, and similarly at long wavelengths, okay, low frequency on the right side of the graph, the energy per photon is very low. Okay, so there's not much energy being carried out. And that, in a nutshell, is how quantum physics explains quantization, why radiation comes in discrete packets called quanta or photons in order to satisfy this graph here. That was the only explanation that Max Planck could come up with. Even though it was disliked a lot, it actually worked.